Hello and welcome back to chemistry practice. So today we're going to tackle something called percent yield. And you may have noticed one thing about chemists. They seem to like percents a lot. We've already gone over percent air and percent composition. So now we have percent yield. To be honest, I think the best way to explain this is simply to do a problem. So I'm going to work through this problem, and at the end I'll go back and explain percent yield. But let's go ahead and look at this. Chlorobenzene, C6H5Cl, is used in the production of chemicals such as aspirin and dyes. One way that chlorobenzene is prepared is by reacting benzene, C6H6, with chlorine gas according to the following balanced equation. Oops, so we know this is balanced, which is good. And we have the equation here. What is the theoretical yield if 45.6 grams of benzene react? So, first of all, this question here is simply a mass-to-mass stoichiometry problem, which we've already done. People get tripped up when it says theoretical yield. They're like, what does that mean? Really, this just means if I put 45.6 grams of benzene into this reaction, how many grams of chlorobenzene will I get? Or how many liters of hydrochloric acid or whatever. So this is a mass-to-mass stoichiometry problem. They're just using slightly different terminology. Let's go ahead and do this problem really fast. Start with your given. We're given 45.6 grams in the upper left-hand corner. 45.6 grams of benzene, C6H6. Let's convert this to moles. 1 mole of benzene, C6H6, equals about 78.12 grams of benzene. Now let's build our mole ratio right here. So I'm going from benzene, and it's asking me how much chlorobenzene do I get. Sometimes you have to read these things closely to kind of figure it out. So here's benzene, here's chlorobenzene. Keep in mind this is balanced, so this is 1 mole, this is 1 mole. So it's a 1-to-1 ratio. 1 mole of benzene, C6H6, produces 1 mole of chlorobenzene, C6H5Cl. Now we need to take this to grams. So 1 mole of C6H5Cl, go get my molar mass from the periodic table, is about 102.569 grams of chlorobenzene. Okay, let's see if our units cancel. Grams of benzene, moles of benzene, moles of benzene, moles of chlorobenzene, and I will end up with grams of chlorobenzene. So if I do this math, 45.6 divided by 78.12 times 112.569, I will end up with around 65.70 grams of chlorobenzene. If the actual yield is 63.7 grams of chlorobenzene, calculate the percent yield. Okay, so now we have an equation. Percent yield equals actual yield divided by the theoretical yield times 100. So our actual yield, and what the actual yield means is if I do this reaction, if I do this lab, This is what I actually get. They'll normally give this to you. I actually got 63.7 grams. Now, in a perfect world, if I did it perfectly and everything worked out perfectly, I should get 65.7 grams. That would be the theoretical yield. So normally the actual is given, and the theoretical is going to be your mass to mass or mole to mass or whatever calculation you do up here. So actual yield is 63.7 grams. Theoretical yield is 65.7 grams times 100. Now if I do this math, I will end up with 96.95% or so. So my percent yield for this reaction is 96.95%. And that's a brief introduction into percent yield. Let's go ahead and do one more problem here. When carbon disulfide burns in the presence of oxygen, sulfur dioxide and carbon dioxide are produced according to the following equation. Now you should always make sure this is balanced, and it is. What is the percent yield of sulfur dioxide if the burning of 25 grams of carbon disulfide produces 40.5 grams of sulfur dioxide? So let's do this first. The percent yield of sulfur dioxide. So we're looking for sulfur dioxide, but they're giving us carbon disulfide. So let's get the theoretical yield first, which is simply a mass-to-mass stoichiometry problem. They give us 25 grams, 25.0 grams of carbon disulfide. Let's convert that to moles. 1 mole of carbon disulfide. I'll go to the periodic table to find my molar mass. 76.143 grams. Now let's do a mole ratio. This is what I'm given. This is what I want. There's no coefficient here, so this is a 1 and this is a 2. So 1 mole of carbon disulfide equals 2 moles of sulfur dioxide. Now we need to convert this back into grams to find the theoretical yield. Although this is a gas, so I guess I could do liters, but it doesn't really specify liters here, so I'll just go to grams. 1 mole of sulfur dioxide. I'll go find the molar mass of sulfur dioxide is around 64.06 grams of sulfur dioxide. Now, if I do this math, I'm going to end up with around 42.07 grams of sulfur dioxide. So what is this number here? This is the theoretical yield. If I perform this experiment and everything goes perfectly, theoretically I should get 42.07 grams of sulfur dioxide. However, they gave us the actual yield. So I actually got 40.05 grams. So I will put my actual yield on top, 40.05 grams, divided by my theoretical yield, 42.07 grams, multiply it by 100 to get a percent, and I should get around 96.27%. This is my percent yield for this equation right here. Okay, let's move down to the second part. What is the percent yield of carbon dioxide? So they're giving us a different part of this equation. The percent yield of carbon dioxide, if 2.5 moles of oxygen react and 32.4 grams of carbon dioxide are produced. Well, Now, instead of giving us grams right here, they're giving us moles. Actually, this is a basic stoichiometry problem. Instead of grams to grams, it's going to be moles to grams. So our given is 2.5. Put your given up in the top left corner. 2.5 moles of, it says oxygen here, but keep in mind oxygen is O2. In our equation it's O2. It's diatomic. And I've seen students miss this because I'll put oxygen, and actually you can't miss it here because you're not converting to grams, but I have seen students miss it when they convert this to grams. They don't put O2, so their molar mass is off. Be careful with the diatomic gases. Okay, we have 2.5 moles of oxygen. Now let's build a ratio. This is our given. This is what we want. The coefficient here is 3. So 3 moles of oxygen. There's no coefficient here, so it's a 1, equals 1 mole of carbon dioxide. Now we're going to have to go to grams. They're giving us grams instead of liters here. So 1 mole of carbon dioxide equals around 44 grams of carbon dioxide. If I do the math on this, I'm going to get somewhere around 36.67 grams of CO2. So what does that mean? My theoretical yield for this equation is 36.67 grams of carbon dioxide. If everything goes perfectly, this is what I should get. However, I didn't get that. I got 32.4 grams. So in that case, I'll put my actual yield, 32.4 grams over 36.67 grams and multiply by 100. If I do this math, I'm going to get around, running out of room here, around 88.36%. This is my percent yield. Okay, I hope that helps you understand basically what percent yield is. We're going to do a little bit more examples in some different videos because the percent yield is something I've seen with problems about limiting and excess reagents. They can use it with volume-to-volume stoichiometry. So those chemistry teachers are devious. They like to get tricky. They like to throw in different examples, use previous knowledge, and this sort of throws people for a loop. But yet again, go with what you're known, slowly go through the equation, and I think you'll be successful. So if you have any questions, let me know, and I hope that helps you out.